Pack assembly and safety. In this video, we'll be covering methods to assemble battery packs, examples of wiring and assembly, and legislation around battery packs. Why it matters, because it's useful for problem solving, legal compliance, and essential for pack building. Spot welding. One of the most common methods to connect battery cells. This method uses nickel-plated steel, pure nickel or copper as thin strips, usually 0.1 to 0.3 millimeters thick. We have an example of these strips down in the bottom right hand corner. Now you can use fuse wire, but it's a little bit more difficult to spot weld. This example here is a piece of thin gauge copper wire about the equivalent to the size of a fuse wire that has been spot welded to a piece of stainless steel. Spot welding has a medium setup cost, usually around about $1,000 or below for a decent spot welder. It requires dialed in settings, so it might take a little while to get your machine right depending on the medium that you are spot welding. However, it is a fast process and it has minimal cell heating, therefore making it one of the most popular methods. Here's an example of what spot welding looks like. Starting with the spot welder itself, this is a K-weld connected up to a couple of car batteries. I've set it to 35 joules to weld 0.15mm nickel strip. This is me welding it in real time. Something that you'll notice is quite interesting is the cables are jumping. And that's because they're delivering about 1,500 amps of current for a few microseconds, causing them to physically move. And here's the whole thing in slow motion, where you can see it generating a lot of localized heat for a short amount of time, melting the nickel strip to the cell can. If the spot welder settings are too powerful, you may blow a hole through the bottom of the cell can. You'll be able to smell this before you see it. The cell needs to be disconnected from the pack and put it in a safe place. Then eventually find a way to dispose of it. Sometimes the probes can melt to the nickel itself, making it difficult to pull them off. To mitigate this, periodically clean the probe ends. The probe ends tend to work best when they are rounded off to a ball point, like the ones pictured here, not too sharp and not too flat. The easiest way to round off the probe ends by hand is to put the probe inside the drill chuck and then use a rotary tool which spins the opposite direction as the drill, and then basically work the head of the probe until it starts to round. Depending on your probe material, this may take a bit of time to get through. These ones I'm using are tungsten rods, but eventually you'll be left with a nice round tip. You just want to make sure that it's even all the way around. And once that's done, reattach it to the spot welder. When spot welding, you may come across some battery cells that have stripped insulation. Usually you can just cover the exposed part of the cell with some electrical tape, but in this instance the insulation is stripped right next to the top, so we want to use an insulation gasket. This is a good idea regardless if it's stripped or not, because it does protect the cell from shorting on itself. Here's an example here. We've got a nickel strip that's over the positive terminal, but we can see that the green gasket is providing a barrier to the stripped part of the cell. That stripped section is actually the negative side of the battery, which is so close to the positive. If that insulation wasn't there, it could cause a short circuit. And with this gasket, we can slide it into the spacer. We can see that it fits perfectly and provides great protection from all sides. This is especially useful if you need to solder onto the nickel strip, because the heat from the soldering iron and the nickel strip, if it's on a battery cell can peel away the insulation if it's not protected by a gasket, which ends up pretty much being a short circuit just waiting to happen. Now, if we remember back to our battery cell video, we only have to worry about this on the positive side, because the positive and the negative terminals are so close to each other, whereas the negative terminal includes the entire side of the cell can and the complete negative end. Therefore, we don't have to worry about it short-circuiting it on itself from the negative side. We can see the negative side on this example with the 5 cells on the left, where they just have the purple base insulation and are not covered by any gasket, unlike the 5 cells to the right. Soldering. One of the cheapest methods to connect cells. It's best used with wire or fuse wire. It's a low setup cost, usually less than $200 for parts. It's best to use a high power soldering iron with a chisel tip, because you want to be able to transfer the heat to the solder and melt it very quickly without prolonged heat to the cell. Excessive heat can damage the cell, especially the electrolyte within the cell tends to degrade at about 80 Celsius. However, with quick exposure to a lot of heat, the heat tends to dissipate through the stainless steel can rather than prolonged exposure. Here we have an example of an older pack that has the same kind of cells. Some of them are just in different heat shrink wrap colors, and it has fuse wire that has been soldered onto the cell can. In this image, the fuse wire connects the cells in series, and the copper wire, which is honestly much thicker than it needs to be, is for balancing the cell groups in parallel. Only do this understanding that the excessive heat can damage the cell, especially with poor technique, and you may even ignite the cell if you're not careful. Now, for any builds that I do for clients, I end up spot welding, but for my own personal builds in the past like this, I ended up soldering. And here's a video example of me soldering together a pack for my e-scooter. Here I'm simply prepping the cell cans and the fuse wire with some RMA solder flux, the no clean stuff. Now, in terms of the solder flux to choose, simply refer back to my video on tools for e-bike electronics, where we cover consumables like various kinds of solder and solder flux. And now I'm just using this knife to hold the fuse wire down on the cell can, and with my fat chisel tip very hot soldering iron, just for a couple of seconds I can melt the solder to bond the two together. Now the positive side is a little bit more forgiving because it doesn't directly back onto the electrolyte since that part of the cell can is raised, but with the negative side you have to be a little bit more careful. Where possible you want to try avoid soldering directly on the center of the cell can, and you just make sure you do it for just a couple of seconds and you should be fine. And we can see now it's even cold to the touch because that heat dissipated quickly. And after a very long time of soldering everything together, I had my e-scooter battery pack. This was built back in 2021, and at the time of filming it is mid-2025, and I still use this battery pack daily. This battery pack was an exemplary case that I used in my video on charging and range. It holds up so well even after all of this time, and even after I did a massive range test on it recently. The reason why I mention all of this is because some people argue that soldering cells can really degrade their capacity. Well, 4 years and still having a good range test result proves otherwise. Other methods. Fasteners, nuts and bolts. Typically you only find this on larger cell formats, so larger than our 18650 or 21700s. Sometimes it can be as simple as using metallic plates with holes in them and then bolting them to each other to connect the cells electrically. Then below that we have ultrasonic fuse wire bonding. This is used most commonly in the automotive industry, so you see this on things like Tesla battery packs. It's extremely expensive to get the equipment, but it is very reliable and ultra efficient. And next is using a heavily modified pulsed arc TIG welder, or something akin to a jewelry welder. Now this is not something I've tested myself, and it's probably on par with the cost of spot welding. However, it looks promising for doing very small welds for fuse wires with a minimal transfer of heat. I've got a few experiments to run, but I may have more updates on this in the future. And now I want you to think back to the cell arrangement and the BMS explained video when we explored the wiring of a battery pack, including the cells. If you need a refresher, go have a look at them now. Otherwise, let's go through what it looks like when we break down a battery pack and building one from scratch. Now, I want to preface this next part by saying that battery pack building by itself could be an entire video series. Perhaps I'll make it as an additional module once there is enough demand or once I have enough time for it. So this next part is just to help you get your feet wet and cover all of the stuff that we've gone over in theory already in a more practical example. Here we have a partially disassembled pack that is going to be harvested for cells. I've laid things out here so you can see how everything's electrically wired together, starting with the balancing JST plug that I'm holding that plugs into the BMS. It is connected to the battery cells, and there are 10 strings in total for a 10S or 36 volt pack. Then the B negative wire which heads to the BMS, and then the P negative wire which heads to the battery terminal, and then the C negative wire which heads to the battery charge port. Or the B positive wires which go directly to the pack positive or the last positive in the series groups. And now I'm pulling on the negative balance wire which goes to the pack negative. Now despite all of the different colors on the balance wires, the first one you can treat as negative and all of the rest as positive, because it goes to each different positive of the cell group. Cell group 1, cell group 2, 3, 4, 5, 6, 7, 8, 9 and 10. And then back to the pack positive. To disconnect it all, we simply cut the negative and the positive, then go through and cut all of the balance wires. And now we're just left with the cells on the battery pack. And here I've highlighted how the cell groups are connected together electrically on both sides. Feel free to pause this if you want to go over it in more detail. Our next step of disassembly involves disconnecting all of the cells from each other by dismantling the nickel strips. And then we simply clean the cell cans of any nickel burrs that are stuck to them. From there, we have nice clean cells which we can put aside, ready for cell grading, where we can reuse our high quality cells and discard the ones that we don't need. Now moving on to pack assembly. In this example, I'm building a 4S13P pack, which I designed in Tinkercad and then decided to 3D print the cell holders. From there, I organized all the cells I was going to use based on capacity. I paired the lowest and highest cells into each group and then worked my way towards the middle. In doing so, you balance out the capacity evenly throughout the pack. Once everything was in place, I began spot welding, beginning to electrically connect all of the cell groups together, starting on one side. With the first side done, it's time to flip over the pack and begin the second side. You may notice on the side that I'm using a barrier because it is easy to electrically short circuit since we've already connected the other side. And that's all of the spot welding portion done for this battery pack. The next step is to connect the BMS negative wire to the negative side of the battery pack. From there, we go through and connect the thermal probe, and then from there we begin connecting the balance leads to the positive end of each of the 13 series groups. I'm using tape under each balance wire just as a precaution so the wires can't possibly short out on the previous series groups. The next step was to solder on a wire to the positive end of the battery pack that would be used for charging and discharging from the positive side. After that, I'm placing a few different wires around the battery pack that will connect to the discharge and charge ports. From there, I solder on any extra connectors and heat shrink and seal any exposed wires. And now, as an extra electrical and moisture barrier, I start encasing the entire pack with tape. Where possible, you always want to plan for a snug fit. But the good thing about this pack is the top and the bottom are not touching the case, so the balance wires can't possibly be crushed. And the core is pretty well fixed in place. But to make sure that it doesn't move, the best thing you can do is use some silicone as a semi-rigid binding mechanism to connect the case to the core of the pack. And then from there we simply connect the various screws, and then we fully charge the pack, and then we put it on our battery tester to get the tested capacity, and then charge it again and make sure everything's balanced, and then we have a healthy new battery. Now that we understand how everything fits together, we want to consider a few different safety standards. These may be optional or mandatory based upon where you are in the world. Now you may be asking, okay, do any of these apply to me? So what I've done is put a pre-engineered AI prompt you can use to see if any of those standards apply to you. So the way to use this is you scan the QR code on screen, or that you use the link in the description. The link will open a ChatGPT window with a pre-filled prompt with all of these various different standards. Then all you have to do is hit enter or run the prompt, and then provide your country, state or region, and then run it again. Then it should be able to give you a specific answer if any of these requirements apply to you. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.